Thank you. Good morning, good afternoon, good evening, everyone. Thank you for joining us today. We have an exciting session planned. First, we will have a science talk followed by a Q&A session. You can put your questions whenever you have in the chat. And then we will wrap up with a code demo to see the research in practice. Before we dive in, I'd like to introduce our speaker for today. Sadegh is a postdoctoral researcher in Paul Stoy's lab at University of Wisconsin-Madison Biological System Engineering Department, and he holds a Ph.D. in systems engineering, and his expertise is in remote sensing and machine learning applied to ecosystem science. His recent work includes near real-time monitoring of land surface temperature, carbon fluxes, and water cycle partitioning using geostationary satellite data. Today, Sadegh will be taking us on an exciting journey through his recent research about knowledge-guided machine learning for partitioning evapotranspiration. Sadegh, over to you. The floor is yours. You could start with your science presentation.
Yeah, thank you so much. Let me start sharing my. All right. Thank you everyone for joining in. I'm Sadegh Ranjbar. I'm a postdoc at University of Wisconsin-Madison. I'm working with Dr. Paul Stoy. At the University of Wisconsin, we are like in my research area, my background is coming from remote sensing and machine learning, and we are creating a near real-time system for carbon and water fluxes in a like project called Alive. If you scan this barcode at the bottom, you can see the website, like the Alive website, and like cool projects are uploaded out there, like our publications, our progress right now, and data sets and codes. Today I'm gonna start I'm gonna present knowledge guided machine learning that we created for partitioning ecosystem water fluxes. And first, before going to the study, I'm gonna a little bit talk about like AI and ML in climate science, why we are using AI and ML, and what's like benefits of AI and ML in climate science. First of all, we know that when we as a like scientists talk about climate, we always want to like model some variables and like the climate behaviors, and machine learning and AI is a very great tool for us to do that, and they provide a powerful like environment for us for like prediction, forecasting, and classification, like land cover, and do like some gap filling things or upscaling and downscaling. So it's a very powerful tool for us to use in climate modeling and monitoring. And the main strength of these AI and ML model is like their scalability. We can create models and upscale it or downscale it to a large continental scales, and they high ability to capture very complex patterns, and also we can use high dimensional data, and those machine learnings are very good to handling those data sets. As I was talking about modeling climate, so we have different ways to do that. One of them is like completely pure data driven modeling, and another can be like a physical based modeling. Pure data driven modeling has some advantage and some limitations. For example, they are very flexible, they can capture complex patterns, they are very scalable, but their limitation can be they are like a black box. We don't know what's happening in there. We don't know like how this model is like treating these kinds of feature to get that output that we want. For example, we want to like we want to map like temperature, or we want to map like carbon uptake, and this model is like getting features as an input and do some like training on those features and data sets, and tune like some weights and bias and give us an output, can be like temperature or carbon. And we also can do like some feature importance to see like which feature is more important in these models. But uh, although we can like explain these types of machine learning a little bit, but in final they are completely black box, and we don't know what equations are primarily like are used in these types of like models, what physics are considered, and is this machine really understand the physics beyond the data, or is just repeating some patterns that are happening in our data sets. So these types of limitation uh, bring us to like to physics-based machine, like physics-based modeling, and but also physics-based modeling have its limitation too. For example, first of all, the physics-based modeling also is coming from empirical data that we had, and also the equations that we created based on those data sets that we have. For example, when we like collect data sets in near infrared and also like in red bands across the vegetation areas, we see like the differences between these two bands, and we can like use those information and define some rules that are based on physics and find out the reasons beyond those like data sets, and then after that model it as and use it as a like physics-based modeling. But these models are very interpretable, and they are like grounded on physics laws, but they have its limitations too. They need many of assumptions. For example, one model that I used previously was like my soil moisture model, soil moisture modeling during my master, and it's before using this model, we have to like assume that the soil is bare, or the like soil moisture is within like like a specific bound, or like, and these models are very huge models and need lots of parameterization um, um, and modification to get like to get applied on a like land, and they are not very easily to like do like upscaling or do like continental scale works. And they have lots of uncertainties, and they are not very good at like large scale adaptability. And so these types of like limitation in pure physics-based modeling, as well as the data-driven modeling, bring us to like why how to like combine these two models. So we started to thinking that using the advantage of the data-driven model as well as the advantage of like the physics-based models, how to do that. First, we started at the like data-driven models. They are like very flexible, but they are not concentrate. They are like they sometimes even like cannot understand the very simple rule of like energy closure or carbon closure equations, which are very simple, but the data-driven models even sometimes can understand that. So we started to see where these how these like data-driven models work, and where they are like start to create those equations. And we see that during like the layers that we create for those data-driven models or machine learning models, or also in like their loss functions that they try to minimize the errors, we started to like add in those like physics-based rules that we have as a like as a layers, as a like definition within the model, and also as a like estimation of the error based on those physics based that we know. And so we started to combine these data-driven models and physics-based models, and the KGML idea came out in recent years by combining these two types of modeling approach. and they combine like both. When they combine both, they are like the models are physically consistent. For example, they can like they follow the some simple equations like water energy like closure, or water carbon coupling, or carbon closure, and they are very good and generalizable across the like large scales, because we still are using the data-driven modeling, and they are interpretable more than like the traditional data-driven models, because right now we are using some physics in our modeling. They are data efficient, and they are like coherent across variables. They can like they know that different variables that we are like modeling, how they are like related to each other based on the equations and like the physics that we are using within the model, and they are very robust. For example, this study that you see was done by Leo in 2024, and they like use some physical models to pre-train a data-driven model, and then use the ground data sets to like fine-tune it. Before going through that, let's start with like how can we do like the KGML. The KGML can be done like in three different like ways that I've studied. Like in these three ways, we can add knowledge or physics in the like data-driven models. One way is like to do the pre-training using physical models that we have. For example, we have a physical model that knows how like lights, how remote sensing features like near infrared and those features are related to our output. We can use those physical models to create like a large synthetic data sets, and then do training on a machine learning model. When we do this machine learning model, it's like acting exactly as the physical model that we have. It's like a mirror of those physical model, but in a like body of data driven model. Then we can like use our data set, our like real world data set, to fine tune that model. It means that when we are like training a machine learning model, we have like lots of weights and bias to like get trained and get tuned. And when we do like pre-training, it's like when we wanna like start for the fine tuning, it gets a start, for example, at a high accuracy, and it's going to be higher, or it starts at a good accuracy of like fitting on the physics base, and then start with like higher accuracy for like fine tuning, and gets tuned on our data sets that we have. In like in this strategy, there are several benefits that we can have. One of them is that anytime we have like not large data sets in our like training, we can use pre-train physical models. For example, imagine you wanna like train a neural networks model that has like thousands of weights and bias, and we can like train it using like 500 data sets, because it doesn't get very well fitted. But when we like use some physical models to pre-train it, it gets like the weights and bias like estimated at initial values of very good like initial values. Then after that, we can start like using our 500 data set, like a number of data sets, to fine tune it. And in this case, the model would work much better than like using only um, uh, the like training the machine learning model only using those data sets. Another way is to embed the physical equation into the model architecture. For example, when we are like creating a model architecture, we can like define the rules that we have. For example, we can say, okay, I don't want any fluxes to be like any water fluxes to be like negative values. And this model make it like a hard concentrate and make that always true, and always we can get like positive water fluxes. And another way to like add physical concentrate is like adjust the loss function. For example, when we are training a model, we can like choose some targets and choose like a loss like default loss function, like we can say just use MSE or like MAE, like mean absolute errors. And the model goes use those like difference use the difference between like uh, predicted value and actual value, and use it as a like loss function. But sometimes we know that we have like more rules. For example, we want to check if the like predicted water components are equal to, like when we sum them, they are equal to like total evapotranspiration. So we can just use the difference between these and also use it as another like concentrate and loss in our modeling, and try to just minimize those errors too. All right. After knowing some basics about like how KGML came out and how like we can incorporate those rules in our data-driven model, let's go to this study that we've done. This study, the idea behind this study is coming from like a study that has been done with Zhang et al. In 2024. They partitioned total evapotranspiration into evaporation and transpiration, and they didn't uh, like estimate the in canopy evaporation or canopy intercepted evaporation, the water that is like under like canopy and evaporate from there. And we thought, okay, we can use like these KGML models and try to estimate these intercepted evaporations. And we started with some like basic rules when like the intercepted evaporation happens, like after rainfall and after dew events. And the challenge here was that the assumption in our studies that the EI or the intercepted evaporation is usually misattributed to transpiration, because they have like same source and they both are coming from canopy. So after that, we started like to collect the data from the neon network that is already available on the website, and we use some predictors like from those like measurements from the sensors, like soil and air moisture and temperature, radiation, canopy tower temperature, meteorology data sets, and ground heat fluxes, and the time from like the last precipitations or rain, or the time from the last dew event. And then we use like the ZAN 2024 data sets, and for example the ET, T, and E components from conditional eddy accumulation. The ZAN study actually used 5 methods to estimate to like partition ET to T and E, and um, they like concluded that the CEA, or conditional eddy accumulation, or FVS, the flux variance similarity approach, were the most accurate one and the most reliable one. So we started to use a CEA approach, and then we also have the results with like the FVS in our supplementary material from our study to just support our findings. All right, what physical rules and evaluation was done in our study? For the concentrate, we considered mass energy balance and interception thresholds that I was talking about, like time since precipitation or time since dew events, and also non-negatively of the fluxes, like evaporation can't be like negative, or transpiration can't be negative. And we evaluate our approach because we don't have like intercepted evaporation, so we consider a couple of like approach to evaluate this model. First, we compare like prediction with the CEA derived targets that we had. And one important thing here was our assumption. We assumed that um, uh, like transpiration is overestimated because of the intercepted evaporation. So we check like our transpiration versus like the CA derived transpiration, and also our transpiration plus intercepted evaporation versus CA derived transpiration. This shows that for example, if the fit for T plus EI is against like CIT is more than the fit again the fit between T and CA derived T, it shows that the assumption is true. At least we know that the model is working based on our assumption. And we also check statistical distribution, histograms, and like violent plots. And we also check the robustness based on the FVS derived data. Here you can see the high view of the flowchart that we use to like design our model. You can scan this barcode, QR code, and go to the like the data in the and like the data and also the code. And the design here shows that our concentrates like flux balance like positively rainfall and dew triggers for EI. For example, the input data which are coming from neon networks and meteorological sensors, and also our target which coming from like CA or FVS targets from ZAN 2024 data sets. And we did like the data preparations, like align like timestamps and normalizing, and also add time since precipitation and also time since dew events. And then we use an encoder, and then after that a decoder to like estimate each of the component that we needed. For example, here we have 4 component, which is transpiration, intercepted evaporation, surface evaporation, and deposition. And then we use physical concentrates, and which we had like 3 physical concentrates. After that, I will go to the like code and explain this part and show to you that how we use like these physical concentrate in a loss function. Then we compute the losses and go for like the training and back propagation algorithm in like neural network. And then after that we came out with the output. Let me to go to the then I'll be back to this presentation. There are like 3 slides left. Uh, all right. Um, the QR code that I showed you will bring you here, which is the code that we made available for this study. Here you have here you have three files. One of them is like the CSV file, which are the data sets, and another is the KGML ET partitioning, which is the code for partitioning and the KGML code, and another is the README, which explain these files. All right, let's see how the code works. It has like three sections. One is important, like is importing the libraries. And for example, if you are using Colab like me, you can like add your drive here and then import the libraries that are needed. Another section is like the functions for like the methods that we are trying to do, like the partitioning, and another is like running and training part. Okay, for the function here, you can see that as I like show on the presentation too, we have like an encoder from the beginning of our like coding. Then after the encoder, we have like the decoder. Here we wanted to like estimate transpiration, intercepted evaporation, surface evaporation, and deposition. And we also have one features like soft plus. It's like it's working. It's a function that working for like make all the fluxes positive. We have like a forward here forward approach that our model gets its input from. It has a like x as input, which are like the it's like predicting the variables. It's predictors or features that we use to predict our target. And it's also gets the time since precipitation and also time since dew point. Here you can see that we like started with encoding our inputs, the features that we give it, the data that we give it is going to this encoder and give us the age, which is the encoded information. Then these heads or these out, like this decoder part of the code is getting the encoded information and give us like the raw transpiration, intercepted evaporation, surface evaporation, and deposition. And we use like some soft plus that make these like fluxes positive, as I talked previously. And then we also have another physical rule that we considered here. We must like the intercepted evaporation. We said, okay, if the precipitation is less than like 48 hours, or or if the time is like less than 12 hours from last like dew point, consider like considering having like intercepted evaporation, unless we are like considering the canopy is dry. So we use this mask to like define our intercepted evaporation. And then we have like the return of this function that returns our output. After that, we have like Flux data set, which this part is only preparing our data set for input. I'm not gonna like talk about this part a lot. It's just bring our features and our data sets to like more GPU friendly like data sets to like make the training faster, because we are using GPU to train our modeling. And then for the training part, we have like we define a function here. And the important part is here. After like we start like training, we get like the model trained on the like x, which are our input, and time since precipitation and time since dew event. And when we started like training on these, it's going to give us the output that we had. Like output, we define here our outputs as like transpiration, intercepted evaporation, surface evaporation, and those variables. And here we are like computing our losses. Like the first loss is making sure that this equation is like happening. Like we have like the sum of T intercepted evaporation and surface evaporation is equal to like T plus E that are coming from FVS approach. And also the other like loss function is make sure that the sum of all of these four is equal to ET. And another assumption that we consider in our study also is happening here, that we are like having another loss for like we are considering T plus EI is equal to TFVS. And we compute the total loss here as like you can see here the total loss, which is the summation of these three losses. And we use like back propagation algorithm here, and it's a little bit out of this like seminar to talk about. And it's a simple like way to just bring back the loss function to the model, and it starts to like optimize it again, and the optimizer starts to working. And then after that we run like the model, and we get to the like when we like run neural network, especially like the deep learning models, these models starts to like reduce the loss functions. For example, here you can see that the loss is like getting reduced after like each epoch and after each training to just reach to the lower number of like losses. And yeah, this is the code part. Let's get back to the slides. All right. Yeah, after that, yeah, after like training and all of like this study, we came out with like the results. The results show that the KGML can like get like fitted on the data sets very easily and very efficiently, and it also follow the rules that we gave it to it. For example, if you see the subplot A2 here and subplot A3 here, you can see that the transpiration, like the CEA derived transpiration by Zan 2024 study, with like the transpiration that we created here, we can see that here we have like some data sets that are off from like CEA transpiration, which these are the intercepted evaporation that we expected, because we made assumption in our like study that T is equal to T plus EI. And here you can see that when we do like the summation between intercepted evaporation and T, it gets more fitted with CA derived transpiration. And you can also see that on like based on like their difference in statistical R square and RMC. And also we can see like the R square for by like sites, because we trained our model by sites and by site. It's not like training on all of the data sets together. We tried that too, and it's like work out. But since we don't need to like do like upscaling thing and those things, so we didn't need to do that. We just use it because the accuracy was a little bit less, so we we opt to just use like the site level prediction. And in another interesting analysis, we showed that how how evapotranspiration, how surface evaporation, intercepted evaporation, and transpiration working like after each precipitation event or each dew point event, and we saw that how they are like decreasing and which one is like increasing after time. Here you can see that the loss trend, and this red line here shows the loss trend of the data, and the other thing is only showed like the data and its distribution like by hour by hour, and after 48 hours of like precipitation here and dew point here. And the loss is a line that shows the trend of the data set. And you can see that after that the like ET increased a little bit, and after that it starts decreasing after like each precipitation event, and also after each dew event. You can see also all of these starts to decreasing. And if you see like these like trends within the data, like sign, like trend in our data set, those are like coming from like day and night evaporation and transpiration. Yeah, and the take home message here is that AI and ML are powerful, but we believe that they need some physical guidance. And since we can add some like physics within them, it's better to always do that, because at least we know that our machine learning model is interpretable, and we know that how this model is working, how it's like follow the energy balance, for example, follow or like the carbon closure. And the KGML can like bridge the data and theory and improves like the interpretability, and the application are like ecosystem modeling, climate projection, water management, and partitioning, and etc. Thank you so much. Thank you to all of like the contributors, the collaborators, fundings unknown, and thank you so much. Let's go if you have any questions.
Yes, thank you, Sadegh, for the exciting presentation. And we got some questions in the chat, but I see it as direct message to me. Are you able to see the questions? The first one I can see here is about why eating units is watt per square meters.
Let me see. Oh,
Okay.
which one is the first one? I see a lot of.
Let me see.
Is it 215?
Okay. I think the first question I'm saying now is about the why the ET units is watt per square meters, not millimeters. Is it latent heat fluxes? I
Yeah,
can read the question for you.
yeah. We actually we use like energy units in our like study. We didn't like convert it to like water um, units.
Yes, I also understand that the units you got from the eddy current capability data, they are generally reported in watt per square meters. And the second question is, are the neon sites all in the same type of ecosystems? How is AI or machine learning system adapting or adjusting for fundamental differences in ecosystem types? For example, like high dynamics, agri ecosystem versus forest.
Yeah, that's a very great question. Um, First of all, the study that we have done is like site-based transpiration partitioning. It's completely based on each site. And this study shows that how we can use KGML in each site to do the partitioning as a tool, and it's not like doing the the upscaling job. But if we want to like do the upscaling job, we can like train on like different sites. And definitely if we don't have like sites in some like ecosystem that and we definitely would have some shortage in those ecosystems, and we definitely would have like we don't have like enough like data representativeness for those ecosystems. Okay, in this area KGML also can work. For example, if we don't have data in some areas, this is a like common problem in traditional machine learning as data imbalancy. And when we have like data imbalancy, we can like use some physics-based models. As I was like talking in the presentation, we have different ways to like add our add knowledge based into our machine learning modeling. And one of them is like using some knowledge like some physics-based models to like create on those ecosystems and like add their synthetic data set to our data sets. For example, we have like some models that know that those works on different like ecosystems, and we know we don't have enough data sets in those areas. We can use those like the knowledge guide like the physics-based models to add a synthetic data set, to like simulate synthetic data set and use them in our data sets to cover the data imbalance.
Yes, thank you for the answer. And another question is, a common issue for using traditional machine learning models is the poor extrapolation of bias in predicting high or low values. Do you think using the physical constraints could help improve the predictions in these extreme ranges?
Yeah, that's a very great question too, because this is another problem in traditional machine learning models, and also I believe in like KGML models, especially in like the extreme events. But at least we know that these knowledge guided machine learning models can work based on the knowledge that we give it to it. And we know that the model is not only remembering the data set and pattern behind it, it also follow the rules that we give it to it. Okay, so how does this help us? For example, uh, sometimes, for example, we have less data sets in like upper range or down or lower range, but when the model follows our like the machine learning model, like the physics rules that we give it to it, or physics concentrates, it's not like going to underestimate our values or overestimate our values. So it's working better in upper ranges and that and lower ranges. And we have like lots of studies that show that KGML can work better in extreme events.
Okay, we got another question in the chat. It's about since the foundation of the Zell 2024 paper you presented in your presentation in flux variance similarity, FVS and FVS is typically applied to high frequency data like 10 Hz. Do we always need 10 Hz flux tower data for ET partitioning using KG-ML, or can half-hourly flux tower data also to be used effectively with KG-ML for ET partitioning?
Yeah, that's a good that's a very good question. But and the good thing about KGML model is their flexibility. They're like they can get any dimension of data sets. They can get high dimension, lower dimension, and their flexibility is the good thing about them. And here it shows that okay, we have that flexibility, and also we have like the FVS approach, like data sets to use. So we can like it's like combining the physical and the machine learning models. I'm not sure if I'm understanding very well, but based on what I understand, based on the question that you asked, I believe that the flexibility that machine learning gave us in is like is can be used also in KGML models, because the KGML models also are data driven models. They are not like physical based models. They also need to train weights and bias within our models, and they all are data driven models. But the difference is that the physics that we use, they can guide the model to make a better model, or guide the model to at least follow some of the like physical rules that we have. And so the thing is that the base of our model is data-driven model, and data-driven model can get any types of data with gaps, without gaps, and with like data imbalancy. But if we have like large if we have like large gaps in our data sets, or lots of like data imbalancy, we may face some like problems. And those problems also can be covered with physics and with like knowledge that we added, the concentrates as we added to the model.
Okay, I think Wei Jie is a co-host. I guess you are able to talk. You have some questions, right?
Hi, yes. Hi, thank you for the very interesting presentation and the very interesting work. And I have a couple of questions, but I will start with the simpler ones. So what is the DEP in the ET equation? We
Yeah,
have yeah, please explain more about that.
yeah, that's a very good question. It's the position. Let me. It's a deposition. It's like a formation of dew deposition on leaves and surfaces, which is like the water and like in liquid form, and it help us to like uh, because because I we believe that the data set, the ET that is estimated and is measured by the sensors,
Mm-hmm.
they have like some source of errors in them, and those errors those some source of errors can also come from the dew, the like dew element on like liquid form. And we could like call it error and use it as error in our equations, but we consider it as a like deposition, and consider it as a like liquid types of water.
So is that the water flow on the truck, but not on the leaf, or I don't know. I didn't understand. Yeah, I still cannot understand what is the
Yes,
liquid
yes. It's like a falling out of
the trunk.
like it's the water like liquid on the like leaves that falling out of like on the atmosphere, and like
Yeah.
deposition of soil. Yeah.
Okay. Yeah. Thanks. And the second one is because I also read some papers about this FVS. I thought it's like the data-driven partitioning method, and it's not a physical process model, right?
Yes, yes.
So then I was thinking, because currently you are training a machine learning model based on the data-driven model-based estimates.
Mhm.
And I was thinking, how can we explain it's not a black box
Yeah.
method.
That's completely correct. The baseline in our like studies that we like trust in Zhang study, in Zhang et al. Study then, but we have a like innovation here. We wanted to use KGML to like separate intercepted evaporation from transpiration. The innovation is here. It's like uh, it's completely correct. We have like this, the model that we created is completely based on another model, and they also the accuracy is based on the other model. We have to trust that one to like reach to this one. We have to like separate like evaporation and evapotranspiration to evaporation and transpiration to just then we can like do the like separation for the intercepted evaporation and transpiration.
Oh yeah, thanks.
Yeah.
So yeah, so maybe I leave time for others, and I can ask you later. I still have some questions. Yeah,
Yeah, those are a great question.
very much.
Thank you, Wei Jie. And I have two other short questions before the end of the webinar. You use neon data for this research. What gaps in the flux data? Big challenge for partitioning work.
Sorry, I had missed connection. Can you repeat that again?
Yeah, the question is because neon data at least for a third of the measurements in 2017, there were a lot of gaps in the half-hourly data. So was it a challenge for the partitioning work afterwards?
Yeah, well, we didn't have like any problem with the data gaps uh, because first of all our data our like model wasn't like a time series model. If definitely if we had like some time series analysis, especially like time series modeling that it needs like regular sequence data sets, we would like face some problems. But here we didn't have like any problems with gaps in our data sets. And yeah.
Okay, thank you. And another question is, do you think it's possible to extend the workflow for more study sites? For example, like hundreds of FluxNet sites, what might be the challenge, and would it be very computational expensive?
Yeah, that's a very good question. I believe that computational like cost matters when we are coming to like the real-time monitoring or in like creating maps. When we want to like create one-time components or model one-time components, it doesn't matter. We need accuracy for that one-time components. But when we want to like do the in my opinion actually but when we are like coming to like upscaling across the whole United States, and we need to like have data for every like 1 kilometers every like 5 minutes or every like half an hourly, it's matter very a lot to like know the less computational expensive models. But here we didn't like test our models computations like compared to other types of modeling techniques, but uh, yeah, if you wanna like use 100 data sets in one training set, first of all our modeling is like site-based modeling, site level modeling, not like extra like not like upscaling all of the models or all of the sites or using all of the sites together for training. But if you want to do that, the model can easily handle it, because one good thing in like the presentation, I also mentioned that one good thing about data-driven model is their ability to get like enough like gets high dimension data sets.
Okay, thank you. And we got two other additional questions from Weijie. It's really high level question, I guess. But that's very interesting. First one is about the assumption. You have like T plus EI equal to TFAS. Is it always valid? Do evapotranspiration also happens in the early morning of winter? What do you think about that?
Yeah, the assumption here was that to separate intercepted evaporation from transpiration, and definitely when it happens like in early morning before like even transpiration happening, it can be like a problem in our work, and we mentioned that in discussion.
Yeah, I think you can unmute and talk now.
Yeah.
Can I ask my question?
Yes.
Okay, so my question is about the energy balance closure. So as we know, the eddy covariance flux towers, so always energy balance closure is about 70% or 75%. It's less than 100%. So your modeling also consider this 30% would not be measured with eddy covariance. So you know the flux.
Mm-hmm.
So if I would like to use eddy covariance flux as an input for the models, so eddy covariance based on the energy balance closure is not measuring whole energy for the ecosystems, about 70%, let's say. So what about this 30%? Will your model consider about this 30% or just this 70% energy balance from the eddy covariance?
That's a very great point to raise. Our model is not like it's not like a physical modeling to do that. It used physics behind it. It used like the fact is that it's a data-driven model, and it's a tool to separate intercepted evaporation from transpiration. We have like we had like ZAN study in 2024 that separated transpiration and evaporation, and then we started thinking, okay, why not like intercepted evaporation? We have like intercepted evaporation in after like rainfall or after dew event. So how to separate that from transpiration? And we came out with like this KGML model. Okay, we can like do a simple and like do like a KGML model to just separate intercepted evaporation from transpiration using some simple rules. And definitely, I believe that we are only use that 70% of the like the energy balance that are already measured, and we are not consider the other remaining part.
Okay, thank you. One more question about the ecosystem. During your presentation, you mentioned about the negative values. And so what about this in the wetlands? So my case study is the peatlands. So I have a lot of negative value. So should I discard these negative values from my input?
That's a very good question also. If the thing is that here I did like the site base, and the good thing is that you can always like change the rules. You can change the rules for your case study and see how does it work. For example, one thing in our like study was that we know that we have like negative values. We know that we have like some noises. We know all of those. so we consider like a variable like the position and call it the position. It could be like even like errors in our data sets. We call it like the position and start like modeling it. You can also have some others like variables in your modeling and use that for like the negative values or for like noises in your data sets. For example, you can remove the position and remove also the soft plus that like make the fluxes positive. You can remove those and instead just use error variable to just model errors.
Thank you very much.
Yeah, we are approaching the end of today's session. I don't see other questions in the chat. I'd like to extend a huge thank you to our speaker today, Sadegh, for sharing this interesting research, and also to all of you getting involved with great questions and discussions. So hope to see all of you next time.
Thank you. Thank you, everyone.